Hi guys, Miss Peterson here, and welcome to AP Physics 2 Lecture 2-2, all about the ideal gas law. Okay, so this comes from Unit 2, Thermodynamics. We're going to be talking about the combined gas law and individual gas laws, where they all come from, and how we came up with this whole ideal gas law. Okay, so how are pressure and volume related? This is Boyle's law. Okay, they are inversely proportional. Okay, so you can think of the inversely proportional. Okay, as the volume decreases, if you give the gas particles less room to move, okay, they're gonna run into the walls more. That makes sense. Now, for that inverse relationship, that means P times V is a constant. So we can write this as P1V1 equals P2V2. So if we're at a given quantity of a gas and a given temperature, if we decrease the volume, the pressure will increase proportionately. Okay, and that's how we get this nice inverse curve shape on our diagram here. The graphs of these gas laws come up quite frequently in AP multiple choice problems. Okay, so for example, say we got sulfur dioxide gas. We have it at, consider a 1.53 liter sample. Okay, so V1 is 1.53 liters of SO2 at a pressure. Okay, we got a P1 of 5.6 times 10 to the 3 pascals. If the pressure is changed so that the new pressure, P2, is 1.5 times 10 to the 4th pascals, so went up by an order of magnitude, looks like the pressure about tripled. Okay, what will be the new volume of the gas, V2? Okay, so in order to cause that increase in pressure at a constant temperature, we're going to expect the volume, since the pressure increased by about a third, we're going to expect the volume to decrease by about a third. But let's go ahead and check that. Now, when we're using this type of equation, it's basically just setting up a ratio, so you can use any units, as long as they're the same for both pressures and both volumes. Okay, so if we got that equation, P1V1 equals P2V2, and we're solving for V2, we would divide by P2. So we get V2 equals P1 times V1 divided by P2. So let's go ahead and plug in those numbers. Okay, V2 will equal P1, 5.6 times 10 to the 3rd pascals times V1, 1.53 liters, divided by P2, 1.5 times 10 to the 4th pascals. So there we can see how those pressure units cancel out, and we get that volume to be 5.6 times 10 to the 3rd times 1.53 divided by 1.5 times 10 to the 4th gives us 0.57. 0.57 liters. So yeah, it cut about in third. Okay, cool. Now, what about Charles's law? That one relates volume and temperature. Okay, so volume and temperature are directly proportional, but they are only directly proportional if you're using the absolute temperature. Okay, it has to be Kelvin temperature. Because this makes sense, okay? As you raise the temperatures, the molecules move more. So they spread out if they can, okay? Raise the temperature, they're moving more. You're going to have higher kinetic energy, so more frequent collisions with the walls of the container, more energetic collisions with the walls of the container. So that can push that container out. So let's look at an example here, because I really want to illustrate why the temperature scale matters. Okay, so we have gas at 15 degrees Celsius, okay, and 1 atmosphere, has a volume of 2.58 liters. Okay, what volume? Okay, so we're looking for V2. These are all our ones. What volume will this gas occupy at a temperature of 3 degrees Celsius and a pressure of 1 atm? Okay, so pressure is staying constant. That means we don't really need to worry about it. Okay, and we're looking for the change in volume. Okay, now, if we were just looking at this, an instinct might be, well, since the temperature divided by 5, the volume will divide by 5. Okay, it'll be 1/5 of that. But if we convert to Kelvin, okay, and we convert to Kelvin by adding 273, we can see that in an absolute temperature scale, the temperature definitely did not become 1/5 of what it was. Okay, so it just decreased by a bit. So we expect the volume to decrease by a bit. Okay, we would have, for this one, they are direct relationship. So it's V1 over T1 equals V2 over T2. Okay, this time I'll just plug in and then solve. Either way works. Whatever you are most comfortable with, do it that way. Okay, so V1 is 2.58 liters divided by T1 in Kelvin, 288K, equals V2 divided by T2, 276K. So when we do that math, okay, we got 2.58 divided by 288, and then multiplied by 276 to get 2.4725, so 2.47 liters. Okay, cool. Okay, cool. Oh, and again, that would look like this sort of direct relationship on the graph. Okay, we're at absolute temperature of 0 Kelvin, which is negative 273 Celsius, is when it would have 0 volume. Okay, cool. Okay, cool. Now, what about pressure and temperature? Okay, so these ones are also directly proportional. If a given quantity of gas is held in a rigid container, so anytime you see rigid container, think constant volume, okay? Constant volume. Anytime you have a rigid container, it's going to be at a constant volume. So if you heat it up, okay, as that temperature increases, the pressure is going to increase. Why? Because the particles have more energy, okay? So temperature is proportionate to, so that's what that symbol means, kinetic energy. And if you have more kinetic energy, you're going to have more frequent and energetic collisions. So higher pressure. Okay. In equation form, this one would be P1 over T1 equals P2 over T2. Okay, cool. Okay, cool. Guys, this one, Avogadro's law, gonna totally blow your mind. This says, like, if temperature and pressure are held constant, if you have more moles of a gas, more quantity of gas, it's gonna have a higher volume. It's gonna take up more space. Okay, no way. More gas takes up more space. Duh. Okay. In equation form, remember, this can be thought of as either the n number of moles or capital N, the number of particles. Okay, so for this one, it's directly proportional, so it'd be like V1 over N. 1 equals V2 over N2. Okay, cool. And again, those N's could be number of particles or number of moles. And now you might be wondering, like, okay, so we have all of these gases and they can undergo changes and these things change in relationship to one another. And if we hold one constant, then the other two change. How am I going to remember all these equations? Okay, that was a lot of equations and none of them are on the equation sheet. I'll show you. They are on the equation sheet, but they're all on the equation sheet as the ideal gas law. So now the ideal gas law is PV equals nRT. Now this is for a gas in a single state. Okay, you would not use this whole equation if the gas were changing. Now, depending on what's changing is how we might set up different properties of it. Okay, like if N and T is constant, okay, then nRT would be a constant. And so we get that volume is proportionate to. So that's what that symbol means, proportionate to. Okay. And we can see in that rearrangement, it all looking up. Volume, if you rearrange it, it's 1 over P, with those being constant. With these being constant, volume is proportional to temperature. With those being constant, volume is proportional to number of moles. That's all of them. They're all there in that ideal gas law. Okay, so just defining those variables again. P is pressure. Okay, V is volume. N is number of moles. And T is the temperature. And then the units for all of those. Okay, for pressure, we're normally going to use the Pascal. For volume, the cubic meter. Number of moles doesn't really have a unit. It's like just moles. For the gas constant, the 8.314 joules per mole Kelvin, the energy version of it, is the one we're going to use most often. And for temperature, it must be Kelvin. Okay, because our gas constants are all in Kelvin. So temperature must be in Kelvin. Okay. Okay, but if the ideal gas law just describes a single sample of gas, and then all of these gas laws we're talking about gases changing temperature or volume, where do those equations come from? Oh, wait. We're not there yet. Actually, no, we'll skip. We'll go back up to there. Okay. Often we're talking about that single sample of gas undergoing a process. Okay, so what would be held constant in that situation? So if we're starting from PV equals nRT, okay, R is a constant. It will always be a constant. N is the number of moles. So if you have a single sample of gas, this will always be a constant. Okay, and so if we rearrange that, we get nR equals PV over T. Now, this will always be true for that sample of gas. So if this will always be true, that'll be true no matter where we're at with pressure, volume, and temperature. So sometimes you'll see this written as P1V1 over T1 equals P2V2 over T2. Now, this one is called the combined gas law. Okay, and again, it just comes from if you have a single sample of gas, then this is always going to be true. So it's going to be true in any state of it. And this one I recommend you know how to derive because you'll use it quite a bit. Yep. But number of moles in R isn't the only way you'll actually see the ideal gas law. Often we'll be talking about the kinetic energy or the energy of individual particles. So we'll write it in number of particles, big N, instead of number of moles, little n. So on your equation sheet, it actually looks like PV equals nRT, which is equal to capital N kBT. Okay, so we have N here, which is number of moles, lowercase n. And then we have big N here, which is the number of particles. Okay, so we can remember that big N, or do it this way, the number of moles is always going to equal the number of particles, big N, divided by NA, Avogadro's number, which is 6.02 times 10 to the 23rd. Okay. Now, that means that they're tied to different constants. Okay. R is the gas constant, which is 8.31, and Kb is Boltzmann constant. Basically the same thing, but without this mole unit, okay? So basically, Boltzmann constant is just the gas constant, R, divided by Avogadro's number, okay? So they're all related, and you can see how both of these equations would lead to that combined gas law. Because if your number of moles is the same, then your number of particles is the same. It's just different ways to represent the number of things there. Okay, cool? Okay, cool. Let's look at one more example problem. Okay, in the lungs, thin respiratory membranes separate tiny sacs of air with a pressure of atmospheric pressure. So pressure is 1.00 times 10 to the 5th pascals. From blood in the capillaries, okay? These sacs are called alveoli, and it is from them that oxygen enters the blood. The average radius of an alveoli is 0.125 millimeters, so 0.125 milli means times 10 to the negative 3. So I'm just going to write milli is times 10 to the negative 3 meters. And the air inside contains 14% oxygen. Assuming air behaves like an ideal gas, okay, so we can use the ideal gas law. That P looks like a rho. PV equals nRT. Find the number of oxygen molecules. Oh, we're looking for molecules. That's a particle, not a number of moles. So we'll probably use NkbT instead. So and then it says at body temperature, which is 310 K. Okay, find the number of oxygen molecules in one part. Okay, so there's a lot going on here. Let's see. I know I'm going to be looking for this number of particles. I know my constant, I know my temperature, I know my pressure, and I do have enough information to find my volume. Okay, volume, they are little tiny sacs of air. So we can assume that they are spheres. Okay, so the volume of a sphere is equal to 4/3 pi r cubed. This is on your AP Physics 2 reference sheet. So plugging in our numbers, we have 4/3 times pi times that radius, 0.125 times 10 to the negative 3, keeping it in meters, cubed, gives us a volume of 8.18 times 10 to the negative 12 cubic meters. Okay. And then I'm solving for n. So I'm going to go ahead and rearrange that equation. N will be equal to PV over kBT. And then I'm ready to plug in my numbers. I have my pressure, 1.00 times 10 to the 5th pascals, times the volume, 8.18 times 10 to the negative 12 cubic meters, divided by kB, 1.38 times 10 to the negative 23 joules per Kelvin, times the temperature in Kelvin, 310 Kelvin. Okay, so let's go ahead and math that out. Okay, we have 1 times 10 to the 5th times 8.18 times 10 to the negative 12 divided by 1.38 times 10 to the negative 23 times 310. And you get 1.9 times 10 to the 14th particles. Okay. And I'm sure I could show you how those units would all work out, but it would probably take a while. So feel free to work them out on your own. Remember, a Pascal is a Newton meter. Okay, we got the meters cubed there. We know what a Newton is related to a joule. Okay, it would take a while, but I trust you guys to do it. It gives you that particles. But hold on. Is this the particles of oxygen? No. Okay, this is the total particles in that sac. But only 14% of them are oxygen. So to get the number of oxygen molecules, which is technically O2. It will just be this number times 14% or 0.14. So times 0.14 gives me 2.676. So I'll just say 2.68 times 10 to the 13 molecules. Okay, cool. Okay, cool. That's it for this lecture.